everybody, and welcome to Pedal-Powered Anthropology. Today, we are going to be talking about different dating methods. And no, I don't mean Tinder versus Grindr. No, today we are going to be talking about different ways that scientists can study the geological and archaeological records to learn a bit about the antiquity of the planet and different human artifacts. The first one I want to talk about is carbon dating. The reason I want to bring that one up first is because I think the vast majority of people watching this have probably heard of it before. You might know it as carbon dating, you might know it as carbon-14 dating, you might know it as C14 dating, you might know it as 14C dating, you might know it as radiocarbon dating. All that refers to the same thing, and that is a calculation made to determine the time elapsed since death of an organism based on the relationship between radioactive carbon and stable nitrogen. Let me translate that a bit. Carbon-14 is a radioactive form of carbon that's absorbed by all living things, yourself included, over their lives. Now, radioactive doesn't mean you're going to get a tumor. Doesn't mean you're going to grow extra limbs. It just means that this particular form of carbon isn't stable. It breaks down over time, yielding nitrogen-14. Nitrogen-14 is stable. And the really neat thing about that is that once carbon-14 breaks down into nitrogen-14, the nitrogen-14 just sits there. It doesn't do anything. And a scientist, the chemist and physicist Willard Libby, back in the 40s, demonstrated that you could extract dates based on this decay process because carbon-14 breaks down at a steady rate. And it turns out that carbon-14 has a half-life of about 5,700 years. And you've probably heard the term half-life before. Half-life just refers to the amount of time that elapses before half of a radioactive element has degraded into its byproduct. In the case of carbon-14, in 5,700 years, you're left with equal parts carbon and equal parts nitrogen-14. In another 5,700 years, that remaining glob of carbon-14 is divided again, equal parts carbon and nitrogen-14. Now, seeing as how this is dealing with the breakdown of stuff, carbon-14 does have a finite lifespan, and 5,700 years is nothing in terms of geologic time. And radiocarbon dating has sort of a useful window, sort of a window where we can detect and measure the presence of carbon-14. That's about, historically, about 40,000 years, 44,000 years. More recently, techniques have been refined and all that, and researchers are pushing that to 60,000 years. But needless to say, at some point, there's either no carbon-14 left, or the amount that's left isn't really measurable. But sometimes we read articles where such and such is estimated to be 100,000 years old, or 500,000, or 1 million, or 65 million years old. How do researchers know that? Well, carbon-14 is just one example of the process called radiometric dating. Radiometric, radio refers to radioactive, metric refers to measuring. It's just a way to measure radioactive decay and sort of use that decay as a clock to determine how old something is. And there are a whole mess of different techniques that all constitute radiometric dating. And you should see them toggling across the bottom of the screen right about now. And really, what it comes down to, more or less, is glorified counting. You know, you have an amount of something, you have an amount of something else, and you measure the amounts against one another. And those quantities let us know how much time has elapsed. Now, I say it's the blink of an eye in geological timescales, but 5,700 years is still a pretty freaking long time, and none of us are going to be around in 5,700 years. So how do we know when 5,700 years is just one half-life of a relatively small window of one technique, and there are multiple? There's ice. They did plow this path, though, which is kind of exciting. So how are we supposed to trust that the 5,700-year time span is accurate, let alone 2 or 3 or 200 or a billion-year time spans? Well, there are a bunch of ways that these clocks can be calibrated and tested, and I'm going to give you one nifty analogy right now that'll help you understand the relative accuracy of these clocks. So, if I were to ask you, what will be the date 1 year from today, or what was the date 1 year ago today? And I don't mean a year from right now when I'm recording this, or a year from when I posted it. I mean a year from today, right now when you're watching it. Now, I'm sure that it's not going to take a lot of brain power for you to figure that out. You probably know off the top of your head. Maybe you're pissed off because you thought it was Friday and you just realized it's Tuesday. But beyond that, you probably know with relative ease what the date was a year ago and what the date will be a year from now. And that's because scientists figured out a long time ago the orbit and rotation of the Earth. And one orbit of the Earth around the Sun is a unit of measure that we call a year. You can break down the year a bunch of ways. 1/12 of a year is a month. 1/52nd of a year is a week. 1/365th of a year is a day, based on the rotation of the Earth. 1/24th of a day is an hour. 1/60th of an hour is a minute. 1/60th of a minute is a second. And all of these are based on very concrete measures that will remain the same unless something really dramatic and horrible happens, in which case it won't matter anyway. And similarly, unless something really, really dramatic changes, the ways that scientists observe radioactive decay are not going to change over time. And in fact, they're in some ways more resistant to those changes, because if an asteroid hit the Earth and all of a sudden the Earth is speeding around the sun in like 100 days, we're all dead. It doesn't matter anymore. But the laws of physics that dictate that radioactive decay, they're not going to change. They're happening regardless of whether or not we exist. It's just whether or not we're around to measure them. And so in some sense, radioactive clocks are more accurate, more reliable than our own measures of time. But there are other methods. There are other methods that are used to date things. And I referred to radiometric dating as sort of glorified counting. Some of these methods are literally just counting. They might be tedious counting, but nevertheless, they're still counting. The next one I want to talk about is called dendrochronology. It's one of my favorite dating methods. And it's literally dendro meaning tree, chronology, time, tree time. And you're probably familiar with this method, whether you know it or not. You might not know it as dendrochronology. But if you think back to elementary school or whenever, when your teacher told you, if you go and cut down a tree and count the rings and get 20 rings, that tree is 20 years old. And you know it's exactly 20 years old because you just killed it and there are 20 rings. And you may or may not also remember that the thickness of those rings is directly related to the weather events, the climatic shifts, the environmental pressures that the tree experienced throughout its life. And so looking at these rings, you have a really nifty history. You have a really nifty chronology of, in a relative sense, what life was like for this tree. The availability of nutrients, the availability of sunlight, the availability of water, or the deprivation of any of the things I just mentioned. But if near this tree that you just cut down is another tree that's just been laying there, and you go and look, and that one's 50 years old, how can we figure out when that tree lived and died? Well, it turns out that different trees in the same area respond in the same way to the same environmental events. And so, if you look at this 50-year-old tree, and you see that the final 8 years of its life are identical to the first 8 years of the 20-year-old tree's life, you know that the older tree died when the younger tree that you just killed was 8. Rather than one 50-year-old tree and one 20-year-old tree, 50 plus 20 is 70, minus 8, because you can only use that 8-year overlap once, is 62 years. So you have, rather than two individual trees, you now have an unbroken, literal historical record of 62 years. You know when one tree died, you know when the second tree died based on it, and you can piece together the different types of things that happen to each tree over the courses of their lifespans. And that's dendrochronology. Now, researchers have gone a little bit overboard with it, and rather than a 62-year history, they've sort of looked at trees in different overlapping areas and pieced together an unbroken historical record spanning back almost 11,000 years. That's a long time. And I don't mean historical record figuratively. This is literally a record recorded on a yearly basis in response to the seasons that tell you about the different weather events and environmental stresses that were felt by these trees. All I'm doing now is telling you how to translate it. But it's literally a historical record. And trees aren't the only species that keep historical records. Humans do too. And the nifty thing about that is, when you see something weird happen in a tree ring, and you know how long ago it was, you can go and look at the historical record, and humans wrote down what happened. So you can translate what the trees have said about the history of the planet and correlate it with the historical record that humans have written. And that calibrates that clock, because we know if humans write that such an event happened on such and such a date of such and such a year, and the trees are saying, hey, I responded to that event, and we can count back the rings and see that yes, it was indeed that year, we know that it's correct. And then the next method I want to talk about, it's the last one I'm going to talk about today. It's very similar to tree rings in that it's the accumulation of layers in response to the environment and on a seasonal cycle that are literally just counted by researchers. Only this one is in ice cores. And ice cores are extractions of glacial ice, and researchers just sit there and painstakingly count the different layers that denote different years of snow accumulation. And how it works is basically snow falls in the winter, things warm up a bit. On warmer years, there's a bit more melt, and that freezes more quickly into a thicker ice layer, so warmer years, paradoxically, are denoted by more ice. Colder years are denoted by more snow. As more and more layers accumulate, layers of snow laid down in recent years, recent snow cycles, those layers are what's called neve. And those are sort of considerably denser layers of snow and ice that are just the older snow cycles. And over time, those layers of neve are compressed into a really, really dense, sort of almost glacial ice, but not quite layer that's like impossible to shovel, called fern. Sounds like the plant. It's not spelled like the plant. As you move down through the layers of fern, the pressures increase so much that at some point there's too much pressure and all of the gases are forced out of all the snow and ice. And it's at that point that the fern is transformed into glacial ice. There aren't many imperfections, there are very few air bubbles, and that's why you have that really sort of ghostly blue, otherworldly looking, thick ice layer it's like immediately recognizable as glacial ice. If you've never seen it before, well, now you have. And the fun thing about glacial ice, there are imperfections, there are pockets of air that are trapped. And those pockets of air were trapped when the snow fell. And just for whatever reason, we got lucky. And when the pressures increased, it sort of locked it off on every side, and the air couldn't escape. And that is a perfect snapshot of the atmospheric composition at the time that that layer was laid down. And so when you read things like such and such is the highest concentration of such and such that we've seen in tens of thousands of years, well, this is how we know that it's tens of thousands of years. It's because glacial ice retains in multiple instances exact samples of the atmosphere, of the composition of the air at a given point in time. And all the researchers really have to do is count back those layers and figure out which year it is. I mentioned radiocarbon dating as having a relatively short sort of window where it's effective and accurate. And I mentioned that dendrochronology yields accurate dates within about 10,000 years. And I mentioned that in counting back those 10 to 11,000 years, researchers got a little bit carried away. Well, in the case of ice cores, they really kind of went off the deep end. And ice cores have been counted back almost 800,000 years. That's 750,000 years of just 1, 2, 3, 4. All they're doing is counting the layers. As the pressure increases, those layers get more difficult to see. But nevertheless, they're still just counting them. And all of these dating methods, the tree rings being calibrated with the historical record and correlating with one another, and that being checked and balanced and correlated with carbon-14, and then again with the ice cores, and then with the various different radiometric dating methods and other dating methods all around the planet in different kinds of materials that form and occur in different kind of circumstances. The fact that these jive, that these aren't really in conflict with one another, that's really impressive. Because if one thing is wrong, you know pretty quickly. I mean, if you have 10 things that agree and one thing that doesn't, you're going to check the one thing before you check the other 10. And chances are you're going to find a mistake in that one thing. But for everything to be wrong and still somehow come upon convergent, incorrect dates, that means that not only has something changed in the past that has altered the laws of physics to how we see them today, it has also altered the way in which chemicals react to each other, and as such how we observe them. Because these are different laws of physics, they're different radioactive processes, they're different elements decaying into different elements. They are different environmental processes laying down different layers that we can count. And they all pretty much agree upon overlapping dates. So this is really icy, so I'm just taking it easy. Let me move that. All right, there we go. And so when you read something that gives you a date for something in the deep, deep past, way back in the ancient world, before there were any humans, before maybe even there were any dinosaurs, you can know that the science underlying this is really solid and is bound by the laws of physics in ways that, if that changed, nothing would even exist as we know it. And they're cross-checked and calibrated with one another so that we know with a high degree of accuracy that we're right. And every once in a while we'll find something that turns out it's been contaminated and we throw it away. But for the most part, things just get higher resolution. Methods are refined, there's new technology, sometimes new techniques are developed, and we just get a better idea and better ranges of these dates, and we know with greater accuracy. So when you read some article that says something way back in time is a certain date, you can be pretty confident that these researchers know what they're talking about. Because really, all they're doing, when it comes down to it, is counting something. So that's all for today. If you like the video, click like. If you want more, and I hope you want more, click subscribe. And as always, thanks for watching. I really, really hope that the wind wasn't too bad. I guess I'll be checking in a couple seconds though. Watch this thing have crapped out on me. This would kill me. This would kill me. I don't even know if I can walk past it. This is pretty bad. Whoop. Okay, I made it. I think that's the worst of it.